Speaker is Kantaro Ohmori, and he will tell us about non-invertible chiral symmetry in 3+.
Thank you. Thanks for introduction, and thanks. I start from thanking organizers for carrying this wonderful conference to the last day, and I also thank for giving me this opportunity to talk. So this talk is about ABJ anomaly. As you know, the ABJ anomaly is the phenomena where this the symmetry, chiral symmetry, is broken by the effect of chiral fermion-1 loop, and the divergence with the neutral current gets this kind of contribution. And usually, if this happens, usually said that this symmetry is quantumly broken. However, in this talk, I claim that we can cure this symmetry when the gauge group, this part, is abelian. And the price we pay for that is that if we do that, the symmetry operation is no longer invertible. Okay, so that's a bit unusual, and so that's some generalized symmetry, so-called a non-invertible symmetry. So this fact is found by Choi Lam Shao and also by Craig Cordova and myself in a few months ago. Okay. So global symmetry in the QFT has been generalized over the last decade. And one most famous one in our community is the higher form symmetry, established by this guy Otto Kapusin-Zabak-Willett. And there's a further generalization of that called the higher group, and in particular the Cordova-Dimitrescu interrogator discussed the abelian continuous higher group symmetry in abelian gauge theory, which has the very same kind of spirit with what I'm going to talk about. Okay, another generalization is something called the subsystem symmetry that appears in non-relativistic systems, and that has been extensively discussed in both in the condensed matter literature and in our community. Okay. Then yet another kind of generalization is this non-invertible symmetry, which is the main topic of this talk. Okay, so the non-invertible symmetry has been known in 1 + 1 dimensions essentially, and which is essentially found by Eric Fearinde decades ago, and then there has been many studies. And it's also ubiquitous in topological field theories, but it was not obvious that whether there is examples in higher dimensions in non-topological field theories. So the existence of such was anticipated by Tachikawa several years ago, but really from the last year, there has been extensive activity to constructing the actual examples in the greater than 2 non-topological theories. Okay, so I cannot review any of these nice works by many authors, but I emphasize that this is really an exciting emerging area of research. And I also emphasize that there is no need to go some exotic kind of theories to find non-invertible symmetries. Okay, indeed, in this talk, I will be talking about just the massless QED. Everyone familiar with it, and we will see that there is actually infinitely large non-invertible symmetry in it. Okay, let us start from basics. So the key to the generalization of symmetry is its relationship to the topological operators. So in the simplest case, if you have a conventional human symmetry, then you can define your symmetry operator by just integrating your neutral current over a given codimension surface sigma, getting the neutral charge, and then exponentiate it, okay, with the parameter alpha. Okay, and this symmetry operator is topological in the sense that it doesn't depend on the shape of sigma, and this is a direct consequence of the conservation law. Okay, And the symmetry action in this language is implemented. Symmetry action on the local operator is implemented by enclosing your local operator with this symmetry operator and shrinking this topological operator. You get a phase that is a symmetry action. Okay, and this generalized for an even discrete symmetry where you don't have a J, but you still have this topological operator U for each element of the group. So one important property of these topological operators is the fusion product, which is defined by just putting the two topological operators on top of each other. Okay, and in the case that these symmetry operators coming from conventional symmetry, this fusion product just implements the group multiplication law. And in particular, this in that case, the topological operator comes with its inverse as a group element does. Okay, so in summary, the conventional symmetry is corresponded to the codimension 1 invertible topological operator. Okay, so the generalization of symmetry it can be done by relaxing these conditions. So the higher form symmetry corresponds to dropping this codimension condition. And so namely the P form symmetry is defined by the codimension P plus 1 invertible topological operators. Okay, and this higher codimension means that it acts on a p-dimensional extended operator instead of local operator. And this is a precise formulation of so-called the center symmetry in gauge theory. And for that reason, there is an important application to the problem of confinement. Okay, in this talk, it's the magnetic one-form symmetry in abelian gauge theory, which is electromagnetic dual to the center symmetry, is going to be important. So let me introduce it. So in the abelian gauge theory, you have a field strength F, and you can define a particular current with the two indices in this way. And then this conservation law of this current is nothing but this Bianchi identity for the field strength. Okay, so then you can define, by noticing this, you can define this codimension 2 topological operator by just integrating in this field strength over the codimension 2 surface sigma. I'm working in the 4D, and yeah, and you get this. So this is the symmetry operator corresponding to the magnetic one-form symmetry. Okay, so the non-invertible topological operator is just obtained by just dropping in the both of the constraint, but of course in particular these invertible ones. So okay, so now we say that any topological operator should be thought as a symmetry, generalized symmetry. Why? That's because this topologicalness still ensures us the RG invariant. So we can do the matching, at least we can do the matching of this generalized symmetry in the UV and IR. That's what we want, and this viewpoint is emphasized in this nice paper. Okay, and for such general topological operators, the fusion product looks like this. So here, the right-hand side is sum over the topological operators that you do not see for the group case. So this is beyond group and rather described by category. And one prominent example of non-invertible symmetry is in the 2D critical Ising model. And there is a so-called Kramers-Bonnier duality topological line together with the usual Z2 symmetry line and satisfying this fusion rule. So in particular, this fusion rule is not group-like. And the non-invertibility of this chromosomatic duality line is manifest in its action on the local operator sigma. That is nothing but the spin, the operator measuring the spin at that point. And that actually, this L sigma projects out this local operator sigma. Okay, so you get 0, then 0 is non-invertible, so you see the non-invertibility. Okay. Then I move on to the main topic of the non-invertible chiral symmetry in 3+1 dimensions. And here, for the explicitness, I only talk about the mass SQD. Okay. So, and we think about the chiral classical U1 global symmetry that acts on just chiral part of the electron, rotating say E-2 by some phase. And as all of you know, it suffers from the ABG anomaly. So usually it's said that it's broken, but we can do more. Okay, so one possible attempt to cure this symmetry is by modifying this J by the Chern-Simons term. Okay, but this itself doesn't make sense because this Chern-Simons term is not gauge invariant. Okay, and you can find this in Weinberg, for example. And okay, but I claim that we can do elaborate more when this rotational parameter, this is the transformation parameter for the U1, is 2 pi times a rational number. Okay, so for this parameter we define the naive symmetry operator U p over q defined on this codimensional surface sigma 3 as just the integral of J, basically, but this is due to the ABG anomaly. This is not topological. Okay, and so the naive modification I talked about, if you do that, leads to this thing naively. So you would like to modify this U p over q by this Chern-Simons term for this electromagnetic field composite, but you need the fractional level. Okay, and with fractional level, of course, this Chern-Simons term is not invariant under large gauge transformation. However, it's good to notice that this fractional Chern-Simons term appears to different contexts, namely the fractional Hall state. And this fractional Chern-Simons term is the nothing but the response action for the fractional Hall state with the filling P over Q. So instead of writing in the Chern-Simons term, we can put the fractional Hall state on this surface sigma 3 inside spacetime, and then we expect that this fractional Hall state should automatically cancel the ABG anomaly and makes the defect topological. Okay, so that's the idea. Okay, and to precisely implement the idea, we further notice that this ill-quantized response of the fractional Hall state is due to these topological degrees of freedom of the fractional Hall state that in the IO forms a 3D TQFT. Okay, and so that is the IR fixed point of the fractional Hall state system. To be precise, we use this part of this fractional Hall state TQFT that directly couples to the electromagnetic field, and there's a universal such part identified by these authors called AAQP, and we used this particular TQFT. For example, when P equals to 1, this is just dynamical U1 Chern-Simons theory. Okay, so this U1 field is not the electromagnetic field. You have additional U1 Chern-Simons field on this defect world volume. Okay, so then the modified defect is the stacking of this naive operator integrating J and this fractional whole state topological field theory. Okay, and then this itself is not topological due to the anomaly, and AQP is also not topological if couples to this non-trivial background, electromagnetic background, but the two cancels each other, and this stacking is topological. Okay, and here this AQP is coupled with this bulk electromagnetic field strength F, as it's a ZQ one-form symmetry exists in this AQP TQFT, and so this F is a ZQP one-form symmetry background, and this is nothing but the actual fractional whole state in the real world does. Okay, so from the philosophy I talked before, now we have a non-invertible symmetry. So because we have a topological operator, whatever, so we have a symmetry for the rational transformation parameter. Okay, and the non-invertibility of this topological operator or the symmetry can be seen from the fusion rule. So if you stack this topological operator with the parameter 1 over q and parameter minus 1 over q, okay, then the naive part, integral of j, just cancels out, but you still have this TQFT part. Okay, and the TQFT manipulation tells that you can rewrite this as a sum over this magnetic one-form symmetry defect or symmetry operator with some phase, and the sum is over these two cycles inside this topological operator world volume. Okay, and this kind of sum is called a condensation operator. So the topological operator and its dual becomes the condensation, and this kind of fusion rule is very ubiquitous in non-invertible symmetry in these dimensions. Okay, so this kind of fusion rule is first found by these authors, including myself, in other examples. Okay. Okay, so one good thing about having topological operators is that now we can study its action on any spatial manifold. Okay, by studying this. Sorry, this should be U. This means U, and D. Okay, so we can study its action on any spatial manifold. So the simplest case of the spatial manifold to be the sphere, then this partition function of a topological field theory on sphere is just constant, independent of the background. There is no non-trivial background, and so it's just constant. So this topological operator D is proportional to the naive operator, and that means that the chiral charge is preserved on S3 or its flat space limit R3 as if it were a conventional symmetry, and that leads to a fermion helistic conservation. Okay, and that of the electromagnetic scattering process, which has been known for a long time, but more recently it's also discussed in the global symmetry context. Okay, and this fact that we can ignore Abijah anomaly on flat space reflects the fact that there's no instanton for the abelian gauge group on the flat space. Okay, and this is a peculiarity of the abelian gauge theory. Okay, for other manifold, like S2 times S1, it's more interesting. So the Hilbert space decomposes into the super-selection sector for this magnetic one-form symmetry labeled by this magnetic flux through S2. And then we can compute this partial function for this TFT under the presence of magnetic background. And if this M is 0, if M is not 0 mod Q, then it's 0 and it's 1 otherwise. And this means that this topological operator on this spatial manifold topology becomes a naive chiral symmetry operator times the projection onto M equals 0 mod Q sector. And in other words, the topologicalness of this D tells you that the chiral charge is preserved modulo M on HM. Okay, and this is nothing but the magnetic catalysis, and in this context, it comes from the non-invertibility of chiral symmetry. Okay, so in this way, you can study symmetry action on arbitrary spatial manifold by studying the topological field theory. And closely related thing is that this non-invertible symmetry acts on the 't-Hooft operator, 't-Hooft loop, and when it acts on net, it turns the 't-Hooft loop to a Wilson loop with a fractional charge. So it's fractional, so it should sit on the boundary of the magnetic one-form symmetry operator. So this is magnetic one-form symmetry operator. And okay, and this indicates that when this 't-Hooft loop is actually dynamical, so when there is a dynamical monopole, then that induces explicit chiral symmetry breaking. Okay, and okay, so you can think of such effect as the monopole loop go inside. So and such a term is suppressed by the e to the minus the monopole mass times monopole cosize, which is roughly the worldline action of this monopole. And in the case of 't-Hooft Polyakov monopole, this contribution is actually identified with UV instanton effect. So in UV, you have no abelian gauge theory. You have actual instanton, and that looks like a monopole loop or dione loop in the IO. Okay, and the same non-invertible symmetry is in the Maxwell axion system. So you can regard this Maxwell axion as the SSB phase of non-invertible symmetry. And then in this phase, the potential for the axion is generated by monopole loops. Okay, so that was already found by these phenomenologists, but now we can also interpret that in the language of non-invertible symmetry. So summary. So there are now many examples of non-invertible symmetry in dimension higher than 2. Most of them I couldn't explain, but one of them is the ABJ anomalous chiral symmetry in abelian gauge theory in 3+1 dimensions. And in this, we have to take this transformation parameter to be rational. Then we can cook up the topological operator by stacking the fractional host state onto the naive operator. And we can study the symmetry action on general spatial manifold. Also, we can understand the magnetic catalysis and from this viewpoint. Okay, so the non-invertible symmetry provides a renewed understanding of chiral symmetry. Okay, let me just put the future directions. First eminent task is to find a better formal understanding, and for that a good tool is a symmetry TFT, which you will be explained by Nyaki soon. And another very important thing is to find concrete applications, and one place to look at is phenomenology. There might be new selection rule coming from this, or there might be even a new naturalness, and in that case that will be very exciting. And as Tom already said in his nice talk, that the swampland is another place to find, look for applications. So I stop here. Thank you for your attention.
Thank you very much. Are there questions?
Thanks, Dr. Kantaro. So I think you described the fusion of this non-invertible chiral symmetry labeled by opposite angles, or in other words, the defect and its orientation reversal. What can you say about the fusion when they are labeled by two generic rational numbers?
So, what I did? Something. Okay. Yeah, I think it's not actually understand very well. So the fusion coefficient in general should be a TQFT.
That's right.
And yeah, so in principle you can find it becomes the problem of studying this tensor product of TQFTs. I think it's not fully understood this tensor product among the TQFTs.
But I thought you say there's understanding of what the basic building blocks of this TQFT are. From works from Hota and Cyber.
Sorry, would you say again?
So I thought you said at some point that for this class of 3D TQFTs, there's already some understanding of what the classes are up to isomorphism. But you're saying it's not the case?
Are you talking about the symmetry TFT or?
Yeah.
Yeah.
No, sorry. I'm talking about the 3D TQFT, that gave rise to the fractional Conn-Hall state.
Oh yeah, yeah. Well, you really have to understand this the tensor product and what do you get a P1 Q1 and P2 Q2 and yeah, okay. And there's also the issue of whether it's associative or not. So I think many things is not understood.
Okay, thank you.
Other questions?
So is there some very kindergarten understanding of the 1+1 version of the chiral anomaly with just a abelian field in 1+1 dimensions?
So in abelian, in 1+1D actually, so if for abelian gauge field, 1+1D analog of this is just you have single F.
Yes.
But then you do have the non-trivial monopole background for the abelian even on S2. That means that it's really broken. So in 1+1D, if you do this abelian gauge theory, it's really analogous to this non-abelian case.
But not on R2. Right?
Well, even R2, yes, I think it's very hard to cure. You need something like the fractional charge on this defect. And
thanks.
If there are no further questions, let's thank Kantaro again.